Download this code from codegive.com, link in the description below. OK, let's break down the Mitre CTF 2019 Linux 200 challenge, which focused on exploiting a race condition in a bash script. I'll give you a detailed tutorial, explaining the problem, the exploitation strategy, and provide code examples in bash to demonstrate the vulnerability. Challenge overview, Mitre CTF 2019 Linux 200. The challenge presents a bash script running with elevated privileges, setuid root. The script is designed to manage some kind of data, but it contains a vulnerability, a race condition. This means the script's behavior is dependent on the precise timing of multiple operations, and an attacker can manipulate that timing to achieve unintended results, ultimately gaining unauthorized access or escalating privileges. Understanding race conditions. A race condition occurs when multiple processes, or threads, access and manipulate shared data concurrently, and the final outcome of the program depends on the specific order in which these processes execute. Because the order of execution is often unpredictable, an attacker can exploit this unpredictability to inject their own commands or influence the program state in a harmful way. Vulnerable scenario, check then act. The most common type of race condition that's exploited involves a check then act sequence. The program first checks a condition, example if a file exists, and then based on the result of that check, performs an action, example deletes the file or modifies its permissions. The vulnerability arises when an attacker can change the state between the check and the act. Mitre CTF 2019 Linux 200 specifically, hypothetical example. Since I don't have the exact source code from the Mitre CTF 2019 challenge, I'll create a hypothetical, but plausible, example that captures the essence of the vulnerability and how it would have been exploited. Let's assume the vulnerable script looks something like this. Explanation asterisk. 1 setuid root asterisk. The script is intended to run with root privileges. This is crucial for the exploit to be effective. Setting setuid is a system configuration step, not something you do within the script itself. We'll discuss this later in the setup. 2 target file asterisk. The script operates on the file /tmp/important_data.txt. 3 check then act asterisk. Asterisk. The script first checks if the file exists, if $target_file. Asterisk. If it exists, it checks if the file is writable by the user running the script, if $target_file. Asterisk. If it's writable, the script removes the file, $target_file. The race condition. The race condition lies between the check for writability, if $target_file, and the removal of the file, $target_file. An attacker can exploit this by 1. Creating the /tmp/important_data.txt file initially owned by the attacker's user. The file will be writable by the attacker. 2. Running the setuid root script. 3. While the script is executing, the attacker simultaneously changes the ownership of the file to root. The attack scenario. Here's how the attack unfolds. 1. Attacker creates the file asterisk. 2. Attacker runs the exploit script, simultaneously. Explanation of the exploit. Asterisk. The exploit.sh script first launches the vulnerable _script in the background, and this starts the race. Asterisk. The while true loop continuously attempts to change the ownership of /tmp/important_data.txt to root. This is the critical step in exploiting the race condition. What happens during the race? 1. Vulnerable _script starts. 2. It checks if /tmp/important_data.txt exists, it does. 3. It checks if /tmp/important_data.txt is writable by the user running the script, which is now root because of setuid. Because the original file was created by the attacker and they set the permissions to 644. The root user can only read the file. The if statement will fail at this point, and the file will be kept. 4. Critically, between steps 3 and 4, the exploit.sh script might successfully change the ownership of /tmp/important_data.txt to root. 5. If this ownership change happens during the race window, the vulnerable underscore script will proceed to the rmf command. But, because the file is now owned by root, the attacker's script would likely error out. The goal and the problem. The attacker would like the vulnerable underscore script to remove /tmp/important_data.txt. The problem is that the vulnerable underscore script is set up with setuid root, so that it can delete a privileged file. Now the attacker has access to remove any file on the system, given the full path of the file. How to exploit it? Revised exploit. The strategy to trigger the RMF after root ownership is to have the attacker change the permission of the file /tmp/important_data.txt from 644 to 666 after step 4 of the vulnerable underscore script. The permissions of the file can be changed rapidly in the exploit script. Setting up setuid, important. For this to work, you must set the setuid bit on the vulnerable underscore script. 1. Become root *sudo su. 2. Change the owner *chown root /usr/local/bin/vulnerable underscore script. 3. Set the setuid bit *mod u plus s/usr/local/bin/vulnerable underscore script. Important security note: setting the setuid bit can be very dangerous if the program has vulnerabilities. Only do this in a controlled, isolated environment, like a virtual machine, for educational purposes. Never set the setuid bit on a program in a production environment unless you're absolutely certain it's secure. How to run the exploit. 1. Create the vulnerable underscore script and exploit.sh files. 2. Set the setuid bit as described above. 3. Make both scripts executable *mod plus x/usr/local/bin/vulnerable underscore script exploit.sh. 4. Run the exploit script *./exploit.sh. The exploit will run indefinitely. You can stop it with Ctrl+C. Check if /tmp/important_data.txt has been removed. If the race condition works, it will be removed. Why this works? The critical race. The vulnerable underscore script checks if the file is writable before trying to remove it. The exploit.sh script attempts to change the ownership of the file to root after the vulnerable underscore script has checked for writability and found that it's initially writable, because the attacker owns it. If the ownership change happens quickly enough, the vulnerable underscore script will then attempt to remove a file it no longer has permission to remove. Important considerations and variations. Timing race conditions are heavily dependent on timing. You might need to adjust the sleep value in the exploit.sh script or remove it entirely to increase your chances of winning the race. File creation/deletion instead of changing ownership. Another variation could involve the exploit.sh rapidly creating and deleting the /tmp/important_data.txt file. The vulnerable underscore script might check for the file's existence, but then the attacker deletes it before the vulnerable underscore script tries to access it, leading to an error. Error handling, or lack thereof. The vulnerable underscore script's error handling, or lack thereof, is important. If the rmf command fails, example because the file doesn't exist, the script might continue execution, potentially leading to other unintended consequences. Other system calls. Race conditions can exist in other system calls besides file operations. They can occur when dealing with shared memory, network sockets, or other shared resources. How to mitigate race conditions. Race conditions are notoriously difficult to debug and prevent. Here are some common mitigation techniques. 1. Atomic operations. Use atomic operations whenever possible. Atomic operations are guaranteed to complete in a single, indivisible step, preventing other processes from interfering. 2. File locking. Use file locking mechanisms, example flock, FCNTL, to ensure that only one process can access a file at a time. 3. Mutexes/semaphores. In multi-threaded programs, use mutexes, mutual exclusion locks, or semaphores to synchronize access to shared resources. 4. Careful design. The best defense is careful design. Avoid check then act sequences whenever possible. If you need to check a condition and then perform an action, try to combine them into a single atomic operation. 5. Principle of least privilege. Run your programs with the least amount of privileges necessary. If a program doesn't need root privileges, don't give it root privileges. Revised vulnerable script, with mitigation. Here's an example of how the vulnerable _ script could be modified to mitigate the race condition using file locking. Explanation of mitigation. Flock n200/$lock _ c, this command attempts to acquire an exclusive lock on the lock _ file. And makes it non-blocking. 200 is the file descriptor to lock. The commands within the quotes will only execute if the lock can be acquired. If another process is already holding the lock, the flock command will fail, and the inner block will not be executed. This prevents multiple instances of the script from accessing the file simultaneously, eliminating the race condition. Key takeaways. Race conditions are a serious security vulnerability, especially in setuid programs. The check then act pattern is a common source of race conditions. Mitigation techniques like atomic operations, file locking, and careful design are essential to prevent race conditions. Testing for race conditions can be difficult, as they are often timing dependent and may not occur reliably. Remember to practice these exploits and mitigations in a safe, isolated environment. Understanding race conditions is crucial for building secure software. Good luck.